Okay, so if you haven't seen it, I just went to Google and I did Netherlands shortwave radio, and I clicked on that, and this is the web-based receiver that you can use, and you can actually operate, and you can have some fun with it, listening to all kinds of radio stations and radio enthusiasts talking to each other. Right. Okay, so that's as far as the summary of what we just did before we started to record. Now, today's class, let's see how people are joining in. Okay, good, we're good. Today is... Ta-da! All right. Wireless signal propagation. And as I said in the beginning, before we started recording, this is going to be a nice, cute little lesson, and it is going to be seen nicely with the perspective that we got already from the practical aspect that we have accomplished in the lab with the amplitude modulation circuitry that we have built. Now, as far as some of us we're able to accomplish very clean sine waves and the envelope actually, and sometimes there will be a little bit of a hairiness on the edges. So don't stress about that. You can just tell how easy it is to get some interference into your circuit just by I think it was with Brandon. I was showing that yeah, don't worry about your interference, because look, I could just move my hand closer to the circuit and I can change the way the circuit behaves. So that's the beauty of it. Right. Oh wow. I guess yeah, we're good. Some of us are getting excited. That's good. Whatever that means. Thank you. Okay, so let me just start this thing, and we're going to go through it. And this is not this lesson is not a heavy one, and actually could be a nice and enjoyable one, considering the understanding that we already have, and we can build up on it by looking at some of these slides. So, F5, start the show. Let's start, get the show on the road and go home. All right, wireless signal propagation. Oh, here's the concept of conversion of energy. Let's see what we have here, what's thrown at us as far as the text. Okay, I'm going to, yeah. Electrical conversion of energy, electrical, well, this is the thing about the transducers thing. You remember what transducer is? Transducer is a device that converts one form of energy into another. All right. So let's see what we have on our plate in this one here. Electrical energy must be converted to electromagnetic. So electrical energy must be converted to electromagnetic energy in order for the energy to propagate in free space. Let's get it backwards. In order for the energy to propagate in the free space, then the electrical energy must be converted to electromagnetic energy. Okay, we have that one out of the way. Since air is a good insulator, electromagnetic energy can propagate in the same way as the electric current can travel through copper or aluminum. So, because the air is a good insulator, we can have the electromagnetic waves to propagate, to travel through, much like the audio speaker that converts electrical energy to sound pressure waves. An antenna converts electrical energy into electromagnetic energy So it is a transducer. In both cases, the speaker and the antenna are referred to as transducers. Very mystified type of a word, but now we know what transducer is even more than we knew, well, before. In any wireless system, we need to have both transmitting antenna and a receiving antenna. Well, the antennas are just like those virtual plugs or jacks and plugs. So with the transmitting antenna, you plug into the air, and with the receiving antenna, you fish out what's there in the air. So you plug into the air as well on the receiving end. Now, the existence of radio waves was predicted mathematically in mid-1800s by James Maxwell. That is a very, very heavy name in a good way. Right? We thank that person for a lot of things. All right, electromagnetic waves. An electromagnetic field is made out of electric field and a magnetic field. Whoa, that's why it's called electromagnetic field. These fields exist with all electric circuits. Can't escape that. They're just there. Whenever you have electricity in motion, there will be electric field and there will be magnetic field around it. With the magnetic field surrounding the conductor and the electric field present everywhere there is a potential, difference of potentials or voltage. Wherever there is a voltage, there is electric field. You might remember some of those concepts from the electrical machines that I'm sure you have studied already. All right, now in most circuits, this field energy is returned to the circuit. What does that mean? In most circuits, this field energy is returned to the circuit. The field energy, which means the electromagnetic field energy. And the energy consumed by the circuit is transferred to the load. You might want to read that a few times before, or this here, from here, this whole point here. You can spend a whole lifetime studying this concept. So I'm not going to try to pick it apart too much, because that's a trip. In most circuits, this field energy is returned to the circuit and the energy consumed by the circuit is transferred to the load. So basically, in most cases, we have somewhere close to full energy transfer from one piece of equipment to another, from the transmitter to the receiver, with some small losses in the transmission. Well, the law of conservation of energy must be obeyed. The total energy that we're dealing with is the energy that is being utilized in transmission, being used, and plus the energy that is spent on the losses. So the losses and the energy that is used is going to equal to the total energy that is being provided. So, the law of conservation must be obeyed. Well, must be. It just is. So there go all those YouTube videos that for some reason people do, and I don't know why they do that, when they present some free energy perpetual motion. Okay. In all energy in the fields, if all the energy in the fields is not returned to the circuit, which means is not the part of the useful transmission, we can call this a radiation. So things radiate. Everything that you turn on radiates. Everything that contains electricity, any form of electricity, radiates. Our cell phone, when it idles, it radiates. Our TV receiver or computer monitor, it radiates energy. The keyboard that you're typing on radiates. There are actually some government regulations that when producing certain type of equipment, you have to meet certain amount of energy radiation. You can't exceed in order for you to be legal to actually have it. So everything has to be tested. Even the keyboard you're typing on has to be in compliance with the amount of energy that it releases to the air. All right. Well, human bodies, we have all kinds of electricity flowing through us, and we do radiate in some subtle, small amount. Some people call it aura. Imagine that. We do actually radiate. How, is this some sort of a mystified kind of a thing that, or some of the hippie thing that I'm trying to indoctrinate? No. That's not what I'm talking about. We do radiate energy. And how is that being utilized? Well, motion sensors work based on that. A security alarm motion sensor, well, there are some of them that work on microwaves, but that's a different one. But most of them work on the infrared field that we transmit. We radiate infrared field. That's an energy, and the motion sensor picks up on it. And if that motion sensor sees the energy that we transmit, and if it sees moving from one spot to another, then it triggers. Simple as that. So if you stand there, the motion sensor still sees you, but it's not going to react because you're not moving. As soon as you move, it's going to trigger, which means if the motion sensor is on, and if you throw a chair into the room, the motion sensor will not react because the chair does not, unless the chair is alive. All right, so let's go back to this thing here. If all energy is in the field is not returned to the circuit, we call this radiation. This type of radiated energy is typically not desirable, but can be difficult to, I think it should be and. Okay, so this type of radiated energy is typically not desirable, and it can be difficult to eliminate. It is referred to as electromagnetic interference, EMI. It is also commonly referred to as noise, and it's a man-made noise. Virtually all electronic devices with some clocking circuits will radiate. Well, I would say that all electronic devices radiate, especially with some clocking circuitry, they will radiate. If the source of the radiation is another transmitter, it is usually called as a radio frequency interference. So here is EMI and RFI. Electromagnetic interference, radio interference. The difference? Well, both are interferences. Doesn't matter, you're dealing with sociopath or a psychopath, the knife in the back feels just the same, right? Okay, excuse me. So both of them are interferences, but we cannot distinguish them. Some of them are man-made and some of them just occur. Well, yeah, some of them are more man-made than the others, but we classify them as such. Electromagnetic interference and radio interference. Electromagnetic interference comes from anything that's around us because it's there. Radio frequency interference, most of the time we're going to see that maybe there is some sort of a transmitter that transmits some sort of wireless signal. It's close to us and it's operating on the close frequency range that we are using, and that could be problematic. Um, all right, what are some of the examples of EMI and RFI? Well, EMI, electromagnetic interference. Anything. A fridge could be electromagnetic interference. A Volkswagen drives by. That could be a source of electromagnetic interference. A car driving by has engine produces noise. Excuse me. Then RFI. If you're using a wireless microphone on a stage and you're close by some transmitting tower and some of the frequencies or their harmonics could interfere with your wireless microphone on the stage, so that would be a radio frequency interference, for example. Next slide we have examples of EMI and RFI. EMI, noise created from an audio alternator. Right, see you go. There you go. There goes the Volkswagen. Noise created by a laptop. There you go. Excluding in-band Wi-Fi and Bluetooth, which are desirable transmitters. So these are not considered undesirable because we use that and it's supposed to be there. We made it to be there. Noise created by overhead wires. Next time you drive, I wonder some people still have the AM radios in their cars. Probably not. But if you happen to have one, switch to some radio station that is in the AM band. Usually it will be the talk shows and whatnot. While you're driving close to the high voltage power lines, you're going to hear those. And when you're driving right underneath them, especially. Right? RFI, radio frequency interference. Interference caused by a distant radio transmitter. Noise caused by out-of-band emissions on the transmitter. Noise caused by mixing products of multiple transmitters. And that's why there are some rules and regulations on how far transmitters should be from each other, as far as the frequency bands that they utilize, and it has the rules and regulations also have to do with the power they can transmit and the bands they can transmit. It's all licensed and regulated, because if it were not, nobody would be able to listen to anything, because they would be just interfering. And if you break those rules, if you transmit unlicensed, you can get actually in legal trouble. That's how important things are. Interference caused by Wi-Fi transmitters on same channel. Wi-Fi transmitter on same channel. Well, yeah. Interference caused by signals from two cellular transmitters on the same frequency. Yeah. Many of the above can be difficult to source and reduce, to eliminate. And sometimes they hit you unexpectedly. Like, for example, when I was working for one of the school boards. Oh, solar flares. That's another thing. I'll get to that in a second here. That interference can hit you unexpectedly. When I was working for one of the school boards, I had to go to the school board office, and all of a sudden I can see something weird. All the IT technicians just walking not aimlessly, but just walking with all over the place, look with their laptops open, held in their hands, and just looking at their laptops, and they're walking in different. I go, what's going on? Is there some kind of a game going on or something? Oh no, something happened. There's some sort of unexpected knocked a wireless network down, and they're trying to find the source of the interference. That was it was funny looking. About the solar flares, our sun, mother sun, sometimes gets a little bit mischievous and gets some extra activity happening on the surface. So yeah, they can cause some problems. or challenges, well, it can really interfere with our radio transmissions and receivages, not in a way that it actually directly affects, not directly mixing with the radio waves, but the solar activity, extra solar activity, sometimes creates extra layers in the ionosphere above our Earth. Now, some of the waves, which we're going to look at in the next few slides, some of the waves travel in different ways. Some of them are ground waves, so they just travel around the ground. Some of them are line of sight, so they straight from the transmitting antenna to the receiving antenna. And some of them, they bounce off the ionosphere and in like a zigzag way. They bounce off the ionosphere, hit the ground, and they bounce off the ground and hit the ionosphere, bounce off of it, and so on. And that's how they travel. We can pretty much send those waves all around our planet. Now, when there are some extra ionosphere layers created by the extra solar activity, then some of the frequencies bounce off of that, and usually those are higher. So it used to be years ago when most of the transmissions were analog, so they would be on the same frequencies. Like, for example, the police station in London, where we are, could operate on the same frequencies that the police station somewhere in Vancouver, which is, about 3,000 miles away from us. So usually there is no problem with interference. The waves do not have enough power to travel that far, so no problem. The police radio station, the police radio could operate at the same frequencies as the Vancouver police, and they would not even see each other existing. But when there were those extra solar activities that would create extra ionospheres, then some of those waves would bounce off and travel further. And all of a sudden, the police officer in London was getting a call to some address, and he doesn't, what are you talking about? I know, over there. And then it took them a while to understand that, oh no, I'm in Vancouver, right? I'm not in London. Oh wow, what the heck is going on, right? And by the way, that extra solar activity happens every 11 years. So every 11 years, you're going to have extra solar activity, and that's when some of the special interest groups are going to scream that look, we have to use less plastic straws, because look what happens. And that's happened every 11 years, as long as the Earth exists. So yeah. Yeah, right. Okay. Next slide here. All right. Electromagnetic waves. We are unable to see the electromagnetic waves, with the exception of like the visible to human eyes, which would be the light, which is electromagnetic wave as well. Kind of. There's a little bit more, but nevertheless, it is also classified as electromagnetic wave. In the diagram below, electric field E, these are those arrows pointing up, is shown as being perpendicular to the magnetic fields. Well, we just labeled them as H. So these would be those black arrows here, would be the H's, which is the magnetic field. So I'm pretty sure that from other subjects you also know that the electric field is perpendicular to the magnetic field. All right. Since the electromagnetic field is vertical, in this case here, electromagnetic field is not always vertical, but we're looking at this diagram here, so just keep that in mind. Since the E field is vertical, this wave is said to be vertically polarized. because the electric field is vertical. So this field is vertically polarized. And it would result, it would be a result of a vertically mounted antenna. Now that is beginning to make sense. Let me just give you another visual here. Here's my board. Here's my pan. Here is the ground. Oh, that's a pretty straight line. And the ground, of course, is connected to ground, right? Because it is ground. And here is some sort of an isolator. And here is antenna that is vertically mounted. So the antenna is transmitting this way here. I'm just going to put an arrow here. Here's the propagation, and here's the propagation, and here is the propagation. It just goes all around. It just propagates, right? Well, let's take a look at this direction of propagation. It will transmit a wave, right? Whatever it is, a wave. It's transmitting a wave. So in order to transmit the wave, there is going to be an electricity connected to it, and the other part is ground, right? So there will be an electrical output connected to it. It is going to create voltage in that wire. And the voltage is going to increase and decrease and become the other way. And become, so it's going to go plus and minus, going to grow up, and it's going to come down and going to go plus and minus the other way. And that's how we make wave. So this voltage is pointing this way on that vertically mounted wire. The voltage is the electric field. Well, is the electric field. The voltage will create the electric field, which will be the same direction, vector-wise. So that's why, okay, then if you have, that's why. Then if you have another antenna somewhere else, those waves will, those magnetic waves, electromagnetic waves, or the magnetic waves, were going to propagate and going to hit the antenna, and it's going to create electric field here. So the best way to adjust the receiving antenna in order to get the full benefit of the signals being transmitted, to fully catch that as fully as possible, then it would be a good idea to point the antenna in the same direction so the electric fields match, and you're going to get the most benefit of catching the signal that's transmitted by this antenna here. Okay. So here is how we are presenting those fields. Again, since the electric field is vertical, this wave is said to be vertically polarized, and it would be a result of a vertically mounted antenna. And here's some source when you download of this information. All right, now let us take a look at the circle. It's blue in the center and not so blue outside. It's almost Friday, guys. All right. Isotropic point source. Isotropic means having a physical property that has the same value when measured in different directions. So the value of that would be same as value of that, whatever the value we're measuring, and now we're measuring the power of the signal. Here and here. So isotropic, it just propagates all around. An isotropic point source can be used to describe point source. Could be used to describe an electromagnetic wave that is radiated equally from a point of source in a free space. It just doesn't go one direction. The antenna, the thing radiates all around. All right. Sip of coffee. Catch my breath. We can define a wave front as a surface joining all points on equal phase. Well, the wave transmitted from here, let me just zoom in a little bit, can I? The wave transmitted from this point is going to have a shape. And when it reaches this point here, it's going to be at a certain point of its phase. And when it reaches the same point at the same distance, I mean, another point, that one at the same distance, it's going to have the same phase, all right? And so on. Excuse me. So this would be the wave front. The wave front would travel outwards. Since the wave travels at the speed of light, at some point, in-phase energy will have reached a point of a square of a sphere. Wave front 1. At some point, basically because it travels outwards, at some point it will reach this point, as it will reach any other point, at some other point or point in time. A second wave front, twice the distance from the center, as shown, can be shown. So here's the first wave front, the wave is going outwards, and here's the second wave front that we pick it up. We pick up. I'm getting somewhere with that. Since the area of a sphere is 4 pi r squared, we can say that the power density on the second sphere will be quarter that of the first front. And this is the formula that we're going to use. This is a light class today, light lecture. Power density, which we label as P with the little designation of T, divided by the area of the sphere. So so we have the formula, we have the concept. Let's see here. There you go. Let's see some kind of an example. What is the power received at 100 square centimeters? That's not meters, that's actually centimeters. Area located 5 kilometers from a 10-watt isotropic point center, which could be like a vertically mounted antenna. That isotropic point center. So again, we have the distance from the antenna, 5 kilometers, and the antenna is transmitting the signal 10 watt of the 10 watt power. All right, so what's the power at the 100 square centimeter area located 5 kilometers from that source? Okay, power density equals PT, which was the total power, which would be the 10 watt, divided by 4 pi r squared. And what's the r? Well, you know, that is the 5 kilometer distance, right? And since we're operating in meters, so we're talking about 5,000 meters, because 1,000 meters is 1 kilometer. The calculation is very simple. you look at that, and then we consider that we want to get, if we're going to get the unit, all right, go back here. The power density is measured in the unit of that is watts per square meter. That's important. Watts per square meter. So from that, we're going to get the watts per square meter, and we just have to proportionalize it to translate it into how many watts we're going to get per 100 square centimeters. So meters per, so we just have to translate that into proportions, and the total power in the 100 square centimeters will be it's going to be 318 picowatts. And you know what? That is enough for the antenna. If you got a good antenna, properly set up, it will actually pick up the signal and extract the intelligence out of it, and you can hear the music, or you can hear the voice, or you can have the data transmitted. 5 kilometers, a long distance, right? That's far. Well, not really. Consider, the satellites that are orbiting our Earth, the satellite communications. How far are they? Much further than 5 kilometers. And the electromagnetic waves still have enough energy to travel that far to Earth and be picked up by whatever satellite receiver. Those little satellite dishes mounted on the side of our buildings. That's far, is it? Well, how do you think the signal gets transmitted from the rover on Mars? There's no train going by, no plane going by, that you could put a jump drive on. Look how far that is. So that puts things into some perspective. Now, what does it say? Mr. Hrabinsky said, whom actually set up this course really, really well. Thank you, Mr. Hrabinsky. It is important to note that radiated power drops off at the inverse square function. There we go. Here's the formula. This explains why even a very powerful transmitter will have a very weak signal received at the other end, measured by the significant distance. So a powerful transmitter, when we move away from further and further from it, doesn't take much. We're going to have a weak signal, but it is enough. After all, we just want to hear clear communication. Now, here is an important thing. Safety is an issue. Now, this is no joke, and this is one of those things that safety glasses will not help you. Safety is also an issue, and it's extremely important, like seriously. Right? Safety is an important issue with high-power transmitters, including microwave transmitters. Do not ever open the microwave oven, take the chassis off and try to operate it and see what's wrong with it so you can pinpoint the problem. There's a magnetron there. It's a microwave generator. That thing can make you blind in seconds. It will burn your skin, it will fry your brain. And it doesn't take much. In fact, when some of the first implementations of radar, which included microwave, the safety aspect was not as observed, or some of those things would have to be found out the hard way. And it was in the military that the radar was introduced during the Second World War, when some people were operating or doing maintenance of some of the radars, they would just go and get close to those antennas, and very quickly they found out that you shouldn't do that, that things are serious, because those people who didn't get microwave burns, and it's just basically it fries your skin, fries your body, fries your flesh. Those who were lucky just got blind almost instantly. Not instant, but yeah. So I remember when years ago we did some experiments with in our college actually with some waves, and there was a microwave lab that was set up. But those exercises that we had to perform, they were extremely closely supervised by the instructor, just to make sure that, because it would take seconds, you would put your hand too close to the equipment that you're operating, and you would get a burn on your hand, serious burn on your hand. So I don't want to go overboard and scare you off. But especially when we're dealing with microwaves and high-powered transmitters, then we should have that in mind, because it's a silent killer or invisible killer. Yes, there were some people who are climbing the transmission towers and all, and all that stuff, and that would be considered as something as a confined space, not because you can't get out of it, but there is certain dangers and certain hazards, and a protocol has to be observed, closely monitored, documented, plan of action, and everything that has to do with safety. Transmitters have to be shut down, turned off, same as people who do the maintenance on the high power lines. They walk on them. Those lines have to be turned off for the time of that certain type of maintenance. All right. Radiation burns can be serious, and since most electromagnetic waves are not visible, we need to take extra precautions when working. So knowledge is your most effective weapon against those type of hazards. Waves in the free space on Earth. Wave propagation is impacted by our environment. And there are several effects that impact propagation. Something is missing there. On Earth, wave propagation is impacted by our environment. Let's just stay there. These are similar to those that affect light. Well, light is an electromagnetic wave, and we can see that bounce off the surfaces, well, and whatnot, and travel through things and being slowed down by fog. Excuse me. Well, electromagnetic waves that we don't see, they kind of do the same thing. We just can't see that. But also electromagnetic waves that happens to be in the visible spectrum of humans. All right, okay. The three categories that we have to consider: reflection, refraction, and diffraction. Now, I wonder did you take I think it's called network systems or network cabling, network something. There are three: network system, network cabling, and the third one. I set up three of those, but that's later. Hopefully you're going to get that with me. All right, maybe in the summer. Now, those three, reflection, refraction, and diffraction, they are also important aspects when we are dealing with the optical fiber lines. But with that one, we're dealing with light. Although it's funny because the light that travels through the fiber optics is invisible to us, but it's still considered to be a light. It's because it's within the light spectrum. It's just that invisible to humans. Light. All right? But this here applies. We're talking about the electromagnetic waves that we don't see for sure and that are not considered to be light. All right. Reflection, much like light, not exactly, because different frequencies have tendencies to behave certain different ways. Much like light, radio waves are reflected by a medium. What kind of medium are we talking about? Is it the person who's going to talk to your dead relatives? No, the medium that we're talking about is the physical entity that carries energy, carries the signal. And we consider three basic ones, as we already talked about: fiber, copper, and air. We talked about copper not much, but you deal with copper. Now, when we say fiber and copper and air, that doesn't mean that aluminum is excluded. We just name that copper, which basically we're talking about electrical conductors. And yes, that now aluminum. So in this case, aluminum is copper, even though it's not. All right. Now we're looking at the air type of a medium, as opposed to a electrical or fiber optics. Much like light, radio waves are reflected by a medium. Reflected. Here is an incident wave and here's a reflected wave. It hits a surface and it's a reflecting surface, and if it hits at an angle high enough, and if it doesn't have the oomph, if it doesn't have the power to penetrate that, especially at that angle, it's going to bounce off. If it is going to have enough power, it might puncture through and get refracted, which is going to just puncture through and it's going to change the direction. That's why if you're trying to hit a fish with a spear standing in the water, you will not hit that fish with that spear when you're looking at it, because that fish physically is somewhere different. You're just seeing the refracted reflection or refracted light reflection of that fish, but that is refracted, which means that fish is in a different position. Yeah, that's if you want to hunt for fish. So let's say, much like light, radio waves are reflected by medium. For the total reflection, that waves must be perpendicular to the medium. If you want to get the light or the wave be reflected straight and total reflection, yes, then it has to hit this thing straight on, and it's going to be totally reflected. If not, it's going to be reflected under an angle. Now, the total reflection that is mentioned here is not to be confused with the total internal reflection when we're talking about the light travel through the fiber optics. All right, typically medium absorbs some of the wave. So we do not see 100% reflection. Yes, the surface is going to absorb some of it and it's going to dissipate that energy mostly as heat. For angles that are 90 degrees, we will see reflection where the angle of incidence is equal to the angle of reflection. Well, The angle from what to what? If you draw an imaginary line perpendicular to the surface, so that would be a line like this, that's the line that we measure the angle from. So this angle here is the angle that's measured from that invisible line to that. So that will be the angle here. And that line is called the normal. It's not like it's normal as opposed to weird. No, it is called the normal. That invisible line. All right. For angles, so yeah, okay. If the wave is parallel to the reflective surface, the electric field can be shortened, severely attenuating. So if the wave is parallel to the reflective surface, so if it goes this way here, then the electric field can be absorbed by the ground, so that will be a shorting, and that would be a severe attenuation problem. Just dwell on that idea, please. All right, what are the angles and the names? Okay, so here is the surface. So for example, here is just like traveling of the light. Here is the air, here is the water, and here is the line. And by the way, this line here that joins two mediums, it is called interface. And here is the line, there you go. The perpendicular to the interface, it is called the normal. So over here, the incident wave hits the surface at this angle from the normal to it. So here's the angle of incidence. And if it reflects, it is going to have that angle here. And this is the angle of reflection, which would be the angle of the light of the line here to the normal. This is the normal. The normal. If the wave is able to penetrate the interface, which could depend on two things. More than two things, but mainly the angle that it hits the surface. The lower this angle, the more probability, of course, we're going to have more of a chance of the wave penetrating the interface and going into the other medium. So it means it's going to travel, but it is going to change its angle. And it has something to do with, and I don't want to get into it too much, but something with the index of refraction. Which means is the index of refraction is measured in, is calculated by the speed of light, for example, or the speed of whatever. But in light, it's the speed of light of whatever the medium is. So different mediums slow down the light. Water slows down the light. Glass slows down the light. Crystal slows down the light, and whatever else. With the reference of the speed of light in the vacuum. So in the vacuum, there is nothing to slow the light down. That's the purest environment that's known to us physically. Then if you just put one against the other, then we get something that tells us index of refraction, and it's depending on the angle and depending on the index of refractions of different mediums, and also on the power of that, but mostly on the angle. You're going to either have a reflection happening, or you're going to have a refraction, but if there is a refraction under an angle, then the angle of travel of the wave is going to change, depending on the refractive index of the medium. It might go closer to the normal, or it would go further from the normal. So if we go this way from the air to water, we're going to have the angle closer to it, because water is more dense than the air. If we go the other way, then we're going to move away from the normal, if you go from water to air. All right. So refraction, okay, first with the reflection. Right? So reflection bounces off, boom. Right? Refraction occurs when the radio waves pass through a medium of one density to another. Part of the energy is reflected and part of the transmitted through the water in this case. And here is something else, diffraction. Radio waves traveling in a straight paths can bend around obstacles. Sip of coffee. Excuse me. This is based on the principle that each point is spherical wavefront. On spherical wavefront can be considered as source. That's physics, grade 12. A wave hits something, and that something that's being hit by we consider that as a new source of transmission, the reflective point. So let's take a look at this thing again. Radio waves traveling in the straight paths can bend around obstacles. This is based on the principle that each point on spherical wavefront can be considered as a source of a secondary wavefront. The area lacking coverage is referred as a shadow zone. We'll get to that in a second here. Like, for example, now. All right. So here is a mountain that the bear went over the mountain to see what he could see. I think there was a song. But we're not dealing with a bear here. We're dealing with the antenna. So the antenna transmits the waves. Oh, boom, there's a mountain. So the waves are going to hit the mountain, and that point right here can be also considered as a source of a new transmission, or sort of like that. Right? And the waves are they might bend a little bit or not, but here is what we're talking about, the shadow zone. That we're going to have some dead space here, that the waves are not going to be present. So that's what we're talking about, shadow zones. Diffraction example. We can see that obstacles can be present we can see that obstacles can present a significant issue for coverage. Obstacles can, yes. Is this really an issue in the real world systems? Yeah, depending on where you are. What are the potential solutions? Well, let's not answer that just yet, because we're going to have some answers in the next coming slides. Whoa! We can create cells with different transmitters, and that's how we can cover. So cellular communication, whoa. Something new, right? That's what we call cellular phone. Cellular coverage. All right. There are many ways to address the coverage issue. By design, cellular network architectures, many adjacent cells can address issues related to obstacles. Antennas can be oriented to address specific coverage areas, the orientation of the antennas. More difficult situations require radio repeaters or moving sides antennas. I'll leave that with you. Other challenges created by below ground tunnels. Underground tunnels, below ground tunnels, underground tunnels or basements might need dedicated and potentially costly solutions. Many commercial buildings do have an internal cellular network installed through the Wi-Fi, the wireless access points, which mostly we use for Wi-Fi in our school. But it's not just for so there could be hospitals, and I have installed many of those. So you just, you get a contract and you just go to the hospital or some other large facility. And for the next 6 months, all you do is install the wireless access points all over the place. And those serve more than one purpose. They can translate that cellular phone into the inside of the building. They can also be used for other things, such as something that's called a triangulation. So if any object inside the building is picked up by at least 3 of those wireless access points, then the exact location can be pinpointed of that. So that's an anti-theft system as well. A person, such as a doctor or a nurse, because some of the nurses and doctors, when they come to those hospitals, they get to, once they sign up for their shift, they get their phone, this sort of like a cell phone, to carry with them for the whole shift. And because they have to carry that, their location within the hospital can be pinpointed. Some of the transmitters can be hidden in objects, and they can be triangulated by the wireless access point system within the building. And some of them could be programmed that whatever that thing is not supposed to move out of this room. So if somebody takes something with that device hidden in it, then the alert could be immediate. Right? So it's all all right. So other challenges can be, okay, so let's go back to the slide here. More difficult solutions require radio repeaters. So that internal, not cellular, but internal coverage acts as a signal repeater. And nomen omen, it's a Latin expression for the name of it, describes its function. So a repeater is a device that repeats a signal. Nomen omen. All right. Reflections in an environment can often work as to advantage. Reflections in our environment can often, so we can bounce the signal off certain things. And that whatever the obstacle there, you can find if it's there all the time, you can use that. Or, you can use those, what do you call them? Meteors, to bounce off a signal. And if it passes us close enough, you can bounce the signal of that object traveling close to our Earth. And you got a few minutes of transmission that you can accomplish through that. In building coverage issues. Often large buildings have coverage issues, particularly in the core of the building. The worst area is elevators, which have concrete shafts. There are modeling tools and or site surveys that can be done to determine the magnitude of the problem, which would be the coverage issues. In this image, green is good and red is bad. No coverage, red. So green is good. So that's a modeling software for the signal coverage, wireless signal coverage. Notice towards the middle of the building. So that could be the elevator shafts here. Could be two elevators, one elevator, one elevator. Reflective coatings on windows make situation worse. The solution will require direct base station feed or off-air pickup of the signal of the feed in the distributed antenna system. So basically, internal installation that is connected to some equipment that acts as a repeater. This can be quite costly. Yes, it can. What was it, 2012, when we did the St. Joseph's Hospital in Hamilton, Ontario? We just did one of the wards. And we put, I don't know how many of those Cisco wireless access points in there. And at that time, each of those was $1,000. So yes, you can, just for the device, never mind the wire used, never mind because the wireless devices are wired. You know that, right? They have to be connected to some sort of wire. And the installation and everything else, yeah, it can be costly. Often there's more than one cellular service provider. So we're talking about the issues. So another issue, often there is more than one cellular service provider, as well as the need for public safety coverage. So basically what this one says is that there's all kinds of stuff flying in the air, which can affect the coverage, because some of them could be interfering. Funding for in-building coverage is a significant issue. Who's responsible? I don't know how to answer that. All right. Electromagnetic wave propagation. There are four different modes of propagation of radio waves on Earth: ground waves, space waves, sky waves, and satellite communications. The most significant factor in determining the mode is the frequency. Different frequencies behave slightly different ways. When we are comparing those refractions to light, that's because it's easiest for us, that's the easiest way for us to imagine things that would behave in a similar way, but different frequency waves present themselves with different properties. That's why we classify them. And they will behave in a similar way, but they will not behave in the same way. So ground waves must be vertically polarized, we already know what that means, to prevent shorting to Earth's ground surface. Because if you point the electric field with the parallel to the ground, it is going to propagate to the ground, and it's going to just disappear in the ground. If you want to shoot a water from a hose from point A to point B, you point that hose to point B. From point A, you don't point that hose to the ground and hope for the best. Same with the waves. This type of wave is attenuated by the Earth's surface, and this increases significantly with the frequency. So the problem significantly increases with frequency. Maximum frequency is 2 megahertz. However, the most communication uses much lower frequencies, 30 to 300 hertz for the ground wave. Is that hertz? I gotta check that out. Primary applications is submarine communication. Yeah, and this data is very slow speed. So yeah, that hurts. Space wave propagation. All right, this is the most commonly used mode of radio communications. The propagating wave is transmitted directly from the transmitting antenna to the receiving antenna. Although we are not necessarily talking about line of sight. Line of sight is part of it. What I mean by line of sight means that one antenna has to directly see the other antenna. That's why some of the microwave transmitters are mounted on the highest grounds possible, on the mountain or top of the building or something, so the receiving antenna has to actually see that transmitting antenna. Space wave propagation. This is most common. Yeah, we just talked about that. Now, for the space wave, polarization can be either vertical, horizontal, or both. Doesn't matter. But that has to do with not how the receiving antenna is positioned, because you want to try to position the receiving antenna in the same polarization as the transmitting antenna to get the most benefit of the signal transmitted. It's just that has something to do with shorting the waves to the ground. Space wave propagation. Most terrestrial communications terrestrial communication system known as terrestrial networks use wired or wireless signals to pass through the atmosphere to function on the Earth's surface. So, terrestrial. Most terrestrial communications, like broadcast radio and television, cellular, public safety, telemetry, Wi-Fi, and whatnot, that will be part of the space wave propagation. One of the downsides of this mode is that it's mainly limited to line of sight, mainly. Right? Especially the microwave transmitting and receivers, they definitely have to be line of sight, which means basically one of the transmitting antenna has to see the receiving antenna has to see the transmitting antenna, and it just has to be pointed at it. But we're not talking just the microwave, and we're not talking just the parabolic antennas. Okay, in some cases there might be a reflected wave that can cause issues, as it will have a delayed phase. That is not a very good situation here, because it disperses the signal, especially when, well, if you were on voice, you would, at the receiver, you would hear an echo, because this sound would get there first, and then that one would slightly later. In data, it will be disastrous, because the ones and zeros presented in the time manner and have to be received in the time manner. Some of the extra ones and zeros could be introduced into the transmission, and the transmitter with the digital transmission, it just ceases to exist. It just fails. In some cases, there might be a reflected wave that can cause issues, as it will have delayed phase. Okay, with increasing the transmitter and or the receiver height is one way to increase the transmission distances, right? Because Earth is not flat. Write it down. For the most cellular systems, this is not an issue. And in fact, the design objective is often to reduce transmission distance to keep the cell size small and maximize the frequency used. So yeah, do that. Read that a few times. Skywave, yeah, there you go. So you remember we were talking about the solar activities, Anurag? You were talking about that, yeah. So there it comes. That comes in place. This method is often used for long distance transmissions. Yeah, the transmission uses refraction from the Earth's ionosphere. Well, reflection. From the Earth's ionosphere to increase the distance. Reflection, not refraction, okay? Remember that. For longer distances, skipping can be used to cover thousands of kilometers. Skipping. Skip to my loo, skip to my loo, right here. The signal is transmitted, it reflects off the ionosphere, boom, bounces off the air again, so that's skipping. And you can actually cover the whole Earth like that. You can transmit that and wait. You just do a microphone click, and this thing goes and boom, hits you in the back. Hits the same antenna. If you have the antenna receiver to tune to the same frequency. The downside is that the characteristics of the ionosphere are not constant. Characteristics are not constant, and there are considerable variation from day to night. Yeah, dedicated frequencies are also needed. So to frequency reuse can be limited. Don't know what that means. Which is an issue when high density communication is needed, especially in cellular. Yeah. Now, remember when we talk about the solar activity, extrasolar activity that happens every 11 years? There's an extra layer, which means, well, of course, this here signal, as it bounces, as it skips, it loses power as it goes along, right? Right. If you have an extra layer of ionosphere during that time that the solar activity is extra, then that signal bounces off here and it can travel further distance. So that could be a problem. We see that thing less and less with the digital communication, but keep in mind that the digital communication, yes, our technology, our devices are getting a little bit more advanced towards the digital technology and, stuff like that. All right? However, the basic principles are still the same. It doesn't matter what type of a stereo you're using. You could be paying $20,000 for a home stereo, but the air between the speaker and your ear is the same. It's just air. So the same thing. Even the digital communications, we still use analog ways of transmitting them. So we still have to pay attention to what's going on and how things are done. Satellite communications. This method provides, we're almost done, guys. This method provides reliable communication with well-defined signal paths. Now, we all know that. Drive away from 401 and you lose your cell phone coverage, right? With geostationary orbits, ooh, it is possible to cover much of the Earth. No. It is possible to cover the whole Earth with a cellular communication. However, we all know that we live in Canada, and some of us, most of us, have at one point traveled a little bit towards northern Ontario, for example. And all of a sudden, whoops, there could be some problems with the signal existence. Oh my God, what am I going to do now? I got no cell phone. All right. So the cost to manufacture, well, it's the main thing that decides. So is it possible to cover the whole Earth? Yes. Is the whole Earth covered with the cellular communication systems? No. Why? We don't know why. And if we don't know why, we know why. It's the money. Okay. Applications include GPS. Oh, okay, so that's television broadcast. So GPS is a little different because it's satellite communication. Yeah, it is satellite communication. What we're talking about. So satellite can cover pretty much whole Earth, but not the cellular. A satellite can. That's why some hard-reach spaces areas, people get satellite dishes mounted, and that's how they get the internet, their phone service, everything else. Weather has minimal effect on satellite communications. However, high moisture content, such as heavy rain, can reduce signal. So that's a little bit of a downfall. Well, for many long-distance applications, satellite communication is superior to the skywave. However, it does introduce longer propagation delay. Skip the end. Due to the uplink and downlink paths, signal takes time to travel, so propagation delay is going to happen when we're talking about high distances. Hey, that's the last slide. We can take a look at some of the textbook questions that we have, and additional questions here. What's the difference between EMI and RFI? Answer that for yourself. One is something made, and the other one is something made. Got it? Why is a Wi-Fi signal originating from a laptop not considered EMI, electromagnetic interference? Well, my dear children, because we want this thing to have. We have made it to have it. We have designed that into design. We have worked that into design of that device, and it's part of the device working. So it's not considered as interference. Okay. What type of 4 types of radio propagations? Go back to that. Those slides. Provide 3 examples of structures that can cause a shadow zone. All right. Pretty simple. And you can answer that as well. Shadowing zone or shadow zone in the wireless communication. That's a problem, right? How does the cellular network architecture help address the shadow zone? Well, if you surround everything with antennas, then you're going to see one antenna at some point. Right. Could a television set be considered a source of EMI or RFI? So this goes with the same thing here. That and that are very similar question. One is something made, and the other was made by something else. What would be the way to communicate with someone in northern Ontario who does not have a cellular coverage or terrestrial-based internet? Is there cellular coverage in most northern Ontario? I can tell you, no. Now, traveling through northern Ontario is one of the most beautiful things you can ever do. It's breathtaking. Shadowed by losing some of the coverage of your cellular network. But I still love doing it. It's a good trade-off, anytime. If the power of the power density at 1,000 meters from a transmitter is something. How much closer to the transmitter do we need to move so the power density is twice as that something? Well, you can go to, I think it's the second slide or third slide, we can go to figure that. And there's the formula we can apply. All right, so that's it for today. And as always, I wish you a safe and happy weekend, and I will see you when I see you. Thank you very much. By the way, the lab, AM modulation lab Dropbox is already open, so it's active, so you can drop those labs in, and I just kind of have to mark those. All right, see you when I see you. Thank you.